Hi everybody! Our project is titled Electromagnetic Waves. My name is April Medina and I'm presenting alongside with Visaya Black and Alexis Green. For this assignment, we were asked to explore radiation across a very wide range of energies and wavelengths, from nuclear radiation all the way to radio waves. Because the spectrum spans many orders of magnitude, it isn't realistic to study every type of radiation in equal depth. Instead, our group selected 3 representative examples that best illustrate how radiation is produced, how it interacts with matter, and how it can be detected. Why these 3? The 3 case studies we chose were ionization smoke detectors, visible light, and diffraction on a TV screen, and AM radio transmission. These examples span extremely different energy scales and highlight key contrasts between particle radiation and electromagnetic radiation, as well as the difference between energy per quantum and total power. The big picture is, together these examples allow us to compare how high energy radiation can ionize matter, how mid-energy radiation like visible light exhibits wave behavior such as diffraction, and how very low energy radiation like radio waves can transmit information when produced in large quantities. This comparison helps explain why different radiation have very different biological effects and detection methods. I'll begin with ionization smoke detectors, which use nuclear radiation rather than electromagnetic waves, but provide a useful point for understanding how radiation interacts with matter and how microscopic processes lead to microscopic effects. For part 1, we're focusing on ionization smoke detectors, which are a really interesting example of how nuclear radiation, something we usually think of as dangerous or abstract, is actually used safely in everyday life. This connects directly to the theme of this project, which is understanding radiation across the electromagnetic spectrum and beyond, from nuclear radiation to radio waves, and how different types of radiation interact with matter in every different way. Ionization smoke detectors use nuclear radiation, specifically alpha radiation, which is very different from electromagnetic radiation like visible light or radio waves. Alpha particles are not waves. They're massive particles made up of 2 protons and 2 neutrons. Because of their mass and charge, they interact very strongly with matter, which is why they're useful for ionizing air. Nuclear reaction involved. The nuclear reaction source inside the detector is americium-241, which undergoes alpha decay. During this decay, americium-241 transforms into neptunium-237, emitting an alpha particle. A small amount of gamma radiation is also produced, but the alpha particles dominate the interaction inside the detector. This is a spontaneous nuclear process that occurs at a predictable rate, which makes it reliable for long-term use. Energy per particle. Each alpha particle emitted has an energy of about 5.5 megaelectron volts, which is extremely high compared to photons of visible light. Converting that S to SI units, that's about 8.8 times 10 joules per particle. This high energy is what allows alpha particles to knock electrons off air molecules so efficiently, even though they only travel a very short distance. Activity in order of magnitude reasoning. A typical ionization smoke detector has an activity of about 3 times 10 to the 4th decays per second. Even though that sounds like a lot, the total power output is still extremely small. If we multiply the energy per particle by the number of decays per second, we get a power on the order of 10 to the negative 8 watt power. This is a good example of why energy per particle and total power are not the same thing, which is a recurring theme throughout this assignment. How ionization occurs. Inside the detector, alpha particles collide with nitrogen and oxygen molecules in the air. These collisions strip electrons away, creating a positive ion and free electrons. The presence of these charged particles allow electricity to flow between 2 electrodes inside the chamber. Under clean conditions, this ionization creates a steady electrical current. Indirect detection mechanism. The detector does not directly measure radiation. Instead, it measures the current created by the ionized air. When smoke enters the chamber, smoke particles attach to the ions, reducing their mobility. This decreases the current. When the current drops below a preset threshold, the electron triggers the alarm. Microscopic versus macroscopic effects. On the microscopic scale, what's happening is nuclear decay and ionization of individual air molecules. On the macroscopic scale, this translates into a measurable electrical signal and audible alarm. This shows how microscopic radiation processes can lead to large-scale life-saving effects. Safety considerations. Even though nuclear radiation sounds dangerous, ionization smoke detectors are considered safe. The radioactive source is extremely small and sealed. Alpha particles have a very short range and cannot penetrate human skin. The radiation exposure from the detector is far below natural background radiation levels that we are exposed to every day. The visual evidence. Here we show a picture of an actual ionization smoke detector along with the sketch illustrating the radioactive source ionizing of air and the effect of smoke particles. These visuals help connect the theoretical physics to a real object we interact with regularly. Compared to electromagnetic radiation like visible or ultraviolet light, alpha radiation has much higher energy per particle but is less penetrating. This contrast helps explain why some radiation ionizes matter while other radiation like radio waves does not.
Hey guys, my name is Asaya, and today we're doing part 3, which is visible light and diffraction. So diffraction is basically when a wave encounters an obstacle or an object, and it basically changes the flow of the wave. So for our experiment, we had to flash a flashlight onto a computer screen, and we had to observe the different line patterns, the different light patterns, and the way the light interacted on the computer screen. So for our experiment, we saw that there's lines that were longer than others, brighter than others, different colors, and there was different variations of angles that the light settled on. So the reason for this is because the computer screen has pixel layers that, when the light interacts with it, change the light to go in different angles, and then the colors we saw on the computer screen are because the wavelength of light has different frequencies that determine the colors. So this determines the colors that we see appear on the computer screen when the light hits it. So the radiation that we see here is visible light because we can see the light from the flashlight, and then we can also see the light interact onto the computer screen. So for energy per photon, we just did the energy equation, which is E equals the constants over the wavelength. And for this experiment in particular, we have a bunch of wavelengths, frequencies to choose from for the colors that we can see on the computer screen. So we just did E equals the constants over green. So we did the 550 nanometers for the green frequency, and then we did nanometers to meters conversion, so that would equal 3.611 E negative 19 joules. And then for the electron volts to joules conversion, we ended up getting 2.3 electron volts. And then for the flux, we got the power over the energy. So we just estimated the power for the flashlight, the flashlight energy. So it would be 0.5 joules over the energy from the previous equation. So then we ended up with 1.4 approximately E18 photons a second. And then for the physical processes and the radiation, again, it's visible light because we can see the light from the flashlight, and then we can also see the light from the flashlight interacting onto the computer screen. And then for the physical processes, it would have been diffraction. So for the energy per quantum, again, it would have been energy per photon. So for this example, we just used the different frequencies. So I used red instead. So it would have been 500 nanometers. So it would have been roughly for E negative 19 joules, and then we did the joule to electron volt conversion. So it would have been roughly 2.5 for the electron volts. And then for the flux, it would have just been power over the energy. So it would have been the energy from the previous equation in the denominator, and then the estimate of the energy from the flashlight. So it would have been 0.5 joules on the numerator. So then we would have gotten roughly 1.3 E18 instead of 1.4 E18 because of the difference of the frequencies from the colors that we used for the equations. And then for the detectors, and for the instruments used in the experiment, the instruments were the computer screen, the phone camera, and then the flashlight, and then the detectors were anything with a visual perception of the light, because it's visible light. So it can just be your eyes, it can be the phone camera, or it can also be the computer screen which had the diffraction. So it could have been any of those, and what we're measuring is the intensity of the light or the diffraction. So the emission from the diffraction that we can see from the experiment. So for the sketches, I just did the sketches of the experiment with the flashlight emitting the light onto the computer screen, and then the diffraction on the computer screen. And then I also did an AI prompt with images for the diagrams of the layers of the computer screen, so that we can see the pixelated layers. So we can see how the diffraction works on the first two layers of the computer screen. And that's the end of part 3, and thank you.
Hey guys, my name is Alexis, and I will be going over part 6, which focuses on AM radio waves. So AM radio waves are an example of long wavelength, low frequency electromagnetic radiation, placing them at the far end of the electromagnetic spectrum. Compared to visible light or nuclear radiation, AM radio waves actually carry extremely low energy per photon, yet they play an important role in our long-distance communication. For our research on AM radio waves, our group used a combination of AI tools and trusted websites to help us clearly describe and clarify how AM radios function, as well as generate supporting visual images. This approach allowed us to organize our findings effectively, ensure accuracy, and provide a clear explanation of the behavior and practical applications of AM radio waves, even without conducting a physical experiment. So what does AM radio actually stand for? Well, AM radio stands for amplitude modulation, meaning information is transmitted by varying the amplitude or height of the wave while the frequency remains mostly constant. These waves are produced by oscillating electric charges in a transmitting antenna, which create electromagnetic waves that travel outward through space. Because AM radio waves have very low frequencies, each photon carries an extremely small amount of energy. This energy is far too low to remove electrons from atoms, which means AM radio waves are classified as non-ionizing radiation. They do not damage our DNA or biological tissue, making them safe for our everyday exposure. Although each individual photon has very little energy, our AM radio stations transmit huge numbers of photons every second, allowing signals to travel long distances. One of the most interesting aspects of AM radio is how these waves interact with the environment. Their long wavelengths allow them to diffract around obstacles, follow the curvature of the Earth, and even reflect off the ionosphere at night. This is why you can listen to AM radio in your car while driving through a city or even across the countryside. You can still receive the news, talk shows, or emergency alerts even in areas where other signals might not reach. The physics behind AM waves makes them extremely reliable for communication over these long distances. In conclusion, although humans cannot directly sense AM radio waves, radio receivers convert these invisible waves into sound by detecting changes in amplitude. This combination of low energy per photon and widespread transmissions show how AM radio can be both safe and highly effective. In conclusion to our presentation, I would like to summarize that radiation across the electromagnetic spectrum differs primarily in energy per quantum, which determines how it interacts with matter and its biological impact. For example, high-energy radiation such as alpha particles from nuclear decay or ultraviolet photons used in document authentication carries enough energy per particle or photon to ionize atoms, removing their electrons and potentially damaging DNA or other molecules. Even small amounts of this radiation can cause significant chemical changes. While in contrast, low-energy radiations, including visible light, infrared radiation, Microwaves and long wavelength radio waves cannot ionize matter. Their effects depend on total power, meaning that large numbers of low energy photons can transfer energy as heat, such as how infrared warms the skin, or how microwaves heat our food, or even carry information like how AM radio waves do. They can do all this without causing ionization. Human detectability, on the other hand, varies widely. For example, visible light is directly perceived by our eye, while infrared rays are sensed as warmth, and ultraviolet, alpha particles, microwaves, and AM radio waves cannot be perceived without instruments, requiring detectors such as cameras, thermal sensors, or antennas. Ionization occurs only when a single photon or particle exceeds the electron binding energy of atoms, which explains why increasing the intensity of low energy radiation increases heating or signal strength but does not cause ionization, while even a few high energy quanta can produce chemical or biological damage. That is all for our presentation, and thank you guys so much for watching. Bye!